So it's a pleasure to be here today in this conference honoring Guillermo. And one of the reasons why I'm here is that about 30 years ago, while I was at the World Bank, my boss hired Guillermo to do some consulting for Argentina, and I was asked to work with him with data and analysis. And after a few days working together, Guillermo asked me if I was interested in a PhD program. And so I said yes, that I had an offer from Chicago, but also an admission at Maryland. And that's when he said, if you come to Maryland, I'll make you my research assistant. And I didn't think twice. I stayed at Maryland. That's a decision. I will never regret it. That's exactly what I wanted to say. I don't know the counterfactual, but never regretted. We had almost 30 years of doing research together, be it at Maryland, be it at the IDB when he was chief economist there, or when I come to Columbia to teach in his classes. So you all know about Guillermo's brilliance, but less of you know, I think, about two other characteristics that Guillermo has, which are his generosity and his ability to listen. His generosity he's showed in many ways to many of us here in the Calvo family, with his teaching, with working together in projects, but most of all, listening to what we had to say as if, even when I was a student, and he was already noble material. So thank you, Guillermo, for all this time working together. Thank you for your friendship, and thank you for all the wine tastings, Sarah, you and I have had and will have in the future. Okay. So having said that, let me move on. Now we have a very interesting paper by Fernando Alvarez that will help us put the Calvo model in a much wider and more elaborate context. So it's a pleasure to have you here, Fernando. You have 35 minutes, and then we'll have Jennifer Lau 15 minutes for discussion, and then some questions. Thank you.
So what is a classic, like a classic paper? So think about Maxwell's equations. So how many people go, I'm sort of echoing Jose, and quote the original Maxwell paper for the Maxwell equations of electromagnetism. Nobody really talk about, sort of the title of the paper. Or think about on the electrodynamics of moving bodies by Einstein. No, we just talked about special relativity. Then closer to home, now with analogy, think about like these are the most famous papers in different areas. Think about in modern physics, modern theoretical physics will be the paper by another RG, Juan Maldacena, which is also, nobody quotes the title. It's really weird in the super limit on n infinity. It's all AFD, CFT. Even closer to home to economics, think about GMM. We typically don't quote the title of GMM, and they're all on the same range of citations. All these papers, they're similar. I was looking at that as you said. Perhaps with large, we always look at what is the done formula for the variance-covariance matrix because it's so complicated. But anyway, except that, we just quote GMM. And the same is true for Guillermo's 83 paper. So that's why, you stop counting citation, and it's really a true classic like all these other papers. So I wanted to kind of introduce that, just to give, we all know it, but just I kind of want to acknowledge that, which I think is, just a great idea. Okay, so now let me get to this paper. So this is a paper with Francesco Lippi and Takis Souganidis, a colleague at Chicago. All right, so this is a paper in which it's going to be a simple model, a relatively simple model, in which what we want to explore is strategic complementarity in pricing. And we want to think about a very simple shock, a once-and-for-all monetary shock, and how it gets transmitted to prices. And we want to think about a range of price-setting models that they go from Calvo to basically SS models and Grosov and Lucas. So it's kind of like all the models, a way of thinking about models in between. And this is a paper, kind of an applied theory paper. So we're trying to sort of get some of the qualitative features and then talked about the quantitative differences. So it's a paper on the analytics of this. Okay, so there are a lot of approximations. A lot of simplifying assumptions to try to get into something. In particular, this is strategic complementarity, so we kind of worry about having many equilibriums and how much they react, etc. So we're going to go over that. Okay, there's a large related literature. I'm just going to skip it on the interest of time. Okay, so I'm going to first go through a setup of the monetary economy. You'll see it's a very, very simple setup. Then I'm going to talk about the nature of the strategic complementarity. Then I want to actually stop and go through the case of Calvo pricing in this case, in which it will be very simple to do this, since now we know how to deal with this. But I'm going to basically do it with a kind of different way. I'm going to introduce something that looks like not really right. I'm going to do it in a kind of more complex way, because this is the way I think that then you could do it in more general models, and then it's easier to understand the results for a more general model. I will not talk about kind of really the main results in terms of how you set it up and how you obtain it. I mean, I will not talk about kind of the technology, how to do it. I'll explain the idea of some sort of like the perturbation, meaning like if it's a small shock, then I'll talk about the characterization of the results. But the characterization of the results will be very much similar to the ones in the case of Calvo, and I'll explain the difference, both qualitative and quantitative. Okay, so this is the setup. The setup is kind of simple. It has a representative agent, linear utility on leisure. For this one, it's not required, but it will simplify things. Some sort of money demand. And then there are two features, also standard, but we need to go through the notation. One feature is that goods are aggregated not with a CS, but with a slightly more general aggregator. This is, just to preview, and for those that were in this literature, we sort of know it. This is so that if you have like a static model and you have monopolistic competition, then the optimal markup is not independent of the price of the rest of the firms. Okay? So that's one of the features, and that's this object here, this upsilon. And then the goods that each of the firms have these goods, firms are indexed by K, they produce in this continuous of goods, the goods are used either for consumption or for the produce of an intermediate good that every other firm uses. So what is the point of this, which is in this notation, this little LK? Well, because every firm uses a good produced by every other firm, then if all the other firms happen to have a low price, then I want to have a low price because my cost is low. It's as sort of simple as that, the idea. This is an idea that people explore. It's just to explore this idea. Obviously, it's also more realistic than not having it, but the idea is just so that you want to sort of imitate the price of the other because your cost depends on the price of the other because they are inputs to you. That's the first one. And the second, and this is this alpha floating around. And the second is, as I explained, this is not going to be CS, but potentially something different from CS, as you see there with this upsilon. And this idea is that this is, if you have like a static problem and then you do monopolistic competition, it's not the case that you always want to charge the same markup. The markup will depend on the actual price of the rest of the firms. So you may want to have like, when all the other firms have a high price, you may want to have a different markup, okay? So these two reasons then you want to make you, perhaps it could go either way, that you want to, everything else the same, try to have a price closer to the price of their firms or farther away. It depends on the setting of the parameters. And in terms of what the firms could do, and I know I'm not getting into details, but I'm hoping that the description is enough. The firms have a probability per unit of time of getting sort of this Calvo parameter in which with probability zeta per unit of time, then they could change the price. And with probability 1 minus zeta, then they cannot change the price, or they could change the price only if they pay a cost. So if this probability were to be 0, then they could only change prices paying a cost. If this probability is the fixed cost psi will be very, very large, then it will be exactly like Calvo. So, you could imagine setups that you go all the way that most of the price changes are kind of Calvo-like, most of the price changes are, let me just say, Golosov and Lucas-like, and setups in between. Okay. Now, this is a slide to try to kind of summarize what I said about these two sources of strategic complementarity. Again, which are very common. Think about in the literature for international, the idea of pass-through is very common to try to use this type of demands. But just to motivate how I'm going to write down the simple model, I want to think about a static problem, and this object here, this pi, which depends on my price P and some average price of the rest of the firms, capital P, that's the demand times the price minus the cost. The cost is chi here. So then you think about the optimal pricing, then it will be like a markup that is inversely proportional to elasticity, as in our first micro class, the learning rule. The only issue is that here the elasticity depends in principle on the relative price. Except on CS, this is always the case. So here's a particular, we're going to use a particular setup. And it's also the case that chi, which is the cost, depends on the price of every other firm, just because this aggregate good is an input. So if you think about taking a second order expansion of the profit of a firm that has a price P, when the rest of the firms have a capital price large P, and you do the approximation around a common price, P bar, so P bar will be some sort of a steady state, and then I'm thinking about a price P, and the rest of the firms are not quite at a steady state, then the approximation, the quadratic approximation will have these two parameters. One, it has to do with the curvature of the utility function, and the other one, this has this crucial parameter that I'm going to call theta. What theta measures is the strength of the strategic complementarity. Indeed, for the paper, I could have started here. This is all like an introduction. The paper is going to just have this quadratic utility. I'm just trying to embellish it, okay? Paper is this, actually. It's not the rest. Okay, so, but yeah, I feel like naked without having the other part. Okay, so this theta sort of, it's a number. We make the choice to put a parameter there with a positive value. That means that the strategic complementarity is when theta is negative. Because if you want to make this quadratic term small, how do you do that? If theta is negative, by imitating whatever price the other firms are changing. And this theta could be a number bigger or smaller than -1, because it's the sum of what other authors call the macroelasticity, meaning the share of the common good in cost, and also the elasticity of the elasticity, the so-called superelasticity. It's a sentence with the most elasticities ever. So the elasticity of the elasticity, or the superelasticity. But of course, this could also go the other way around. And we could also have another type of labor supply which will counteract this, and it will go into, instead of complement, substitutes. Okay? Anyway, from now on, and really for the paper, this is some quadratic objective function with a parameter theta. Is that okay? So that's really the... And then I'm going to go to the case of Calvo pricing. All right. Now, this is going to be a bit, you should think that I'm really trying to kill a mosquito with a, H-bomb. But again, it's just to preview the other results. So I'm going to write down the problem from a firm. And I realized that there's a small typo. But anyway, I'm going to write the problem of a firm in which up to cap T, and cap T, it has some reward that is exogenously given. Maybe cap T is infinity. But, and then before that, it has this quadratic objective function. It's trying to minimize it. This quadratic objective function, I'm sorry that I tried to improve the slides at last minute and I made it worse. This quadratic objective function should be a function of x at time s and capital X at time s. I apologize that I forgot that. So you're choosing, so that's the objective function, the one that I announced. It's the expected discounted value of what I announced. Then there is this stopping times, tau bar, exogenously given, which is, when the Calvo parameter, when the exponential distributed times in which you could change prices. It's a bit pedantic to write it this way, I know, but you will see it will pay off. And then at this time, the only thing that you choose is how much to change prices. Okay? So this is a problem in which the times are exogenous, are random, but exogenous given, and you choose these delta j's, which is how much to adjust prices. Okay. It's important that you take as given as a firm the whole path of this capital X. This is what the rest of the firms are doing. I'm going to a particular firm. This function depends on X and T because it depends on your own position. X is the deviation of markup. Remember, it's the object that I showed you before. If your price relative to some steady state, and then you're taking as given the deviation of markups of all the other firms. You're taking as given the entire path. There's a strategic complementarity when theta is negative because you want to follow what the other firms do. Okay, so now think about a time, t, that happens to be a time in which you could change prices. As we all those that have worked on this, which is probably everybody here, know what you're going to do is you're going to choose a price, in this case, that is going to be forward-looking, imitating the average price of the other firms. So this is minus theta, and then integral of the prices of the other firms. So this is the first part. So this is kind of comes from this quadratic nature of it, and you know, you kind of want to approximate. And remember, this theta could be positive or negative. If it is negative, you want to be with the rest, with some discounted value of the rest. If it is positive, you want to get away. If it is 0, you're just setting it at your steady-state value. This theta could be bigger than 1, which means that you may want to be not just on the direction or how they are away from a steady state, but even more than that. People are going to the right. Maybe I want to go a little bit to the right. Or maybe I'm the type that if they go to the right, I really, really, really want to go to the right. That's theta bigger than -1. I'll explore all these cases. Then there is aggregation. This is kind of trivial, but I want to do it in this way, in this pedantic way. Capital X is a cross-sectional average of the little x's, and it evolves kind of in this way that Guillermo sort of came out, which is a fraction of the firms keep the same x as before. It is true they have a random shock, but this shock has expected value equal to 0, so you could just take yesterday aggregate price for those that they didn't change prices, plus all the new ones, and then they get this x star, because all the new ones they get to reprice. This is written in discrete time. Then you can write this in continuous time, which is the next equation. I didn't write this as an ODE. I'm going to keep this as an integral equation. I have some reasons to do this. So the integral equation is that capital X is equal to x0, which is whatever happened in period 0, that will be the MIT shock. In period 0, we're going to start at some value that is different from a steady state. That will decay at rate zeta to the t. And if x star would have been 0, that would be the end of it. But because if x star is not 0, then all the previous periods, there would have been some resetting, so I need to keep track of that. So let me just say it again. At time t, I look at what happened at time 0, and then I looked at what happened every time before time 0. So this is backward looking. The other one is forward looking. Okay? And I'm going to call this term x0 e to the zeta t is the impulse response function if it will be no strategic complementarity, because it will be the case. Now let me put the two equations together. When I put the two equations together, this is a system of two linear integral equations. Xt on one side is a function of all the backward-looking x stars, and x star a function of the forward-looking capital X's. Of course, a sane person would have just written an ODE, but we just don't do that. We just keep the integral equations, okay? Now, the second part is take the x star from the second equation and plug it into the first equation. Then there's no more x stars. Everything is capital X's. But you pay the price as capital X being on both sides. And when you pay the price of capital X being on both sides, you rearrange the terms, and you get the equation that is there. You see that it has this k. K is some known function. It's a function that is written in red below. You could do the computation, let's not, okay? But if you do the computation, you'll get that. This is an equation that has x on the left-hand side, x0 at t, which is what would have happened without the strategic complementarity. The strategic complementarity only enters on theta there, and then it has this other integral equation. So, if this instead of being continuous time will be kind of discrete time, x will be a big vector, x0 at t another big vector, k will be a matrix, and another vector x here, and then you will solve it the way you solve linear systems. Okay? This, in fact, is an equation that is very well understood in mathematics, whatever. It has a name and everything. All right. So I just want to say the properties, and these properties will be shared by the model with fixed costs, where you have to keep track of the entire distribution. Okay, so there are 4 regions of the parameter theta. There's a region, so theta star will be the region in which something kind of happened. I'll describe in a second. Mu1 is some other number. If k will be a matrix, This matrix will have eigenvalues and eigenvectors, and mu's are the eigenvalues of K. This is a gigantic matrix. It has many eigenvalues. If it is an operator, also has eigenvalues and eigenfunctions. So mu will be some eigenvalue. This is the dominant eigenvalue, something that is shown in many papers by this K has similar properties that operators that Jose uses in several of his papers. Okay, so if theta is positive, then there is a strategic substitute. So if I look at the impulse response of output, which is this y theta, then it's smaller than what would have happened if there is no strategic complementarity. I'll explain the intuition later. I just want to say what the results are. Then there is a range when theta is negative, but it's not as big as some other threshold, theta star, where the impulse response is monotone. It starts high because there is a once and for all MIT shock, right? Then basically wages go up. That means real wages are higher in this model. Everybody's kind of working more, but prices didn't adjust. Through time, they will be adjusting. Now, the question is with strategic complementarity, everybody sort of staying, not trying to adjust so much because some people didn't adjust, so that retards the adjustment of nominal terms, and then output stay higher. So in this other region, and I'll show you a graph in a second. Well, let me just show you a graph here. Look at on the left graph, the dotted line. That's a case where strategic complementarity is monotone, and if you fix a little t, a time, it's increasing in the degree of strategic complementarity. So if we have more strategic complementarity, the whole impulse response will be higher, and it's monotone. There is another region where there's another threshold that has to do with the dominant eigenvalue of this operator. I'll explain the economics in a second, but for now, just stating stuff, in which is ham-shaped, the impulse response. Okay? So it's like this. So it means that it doesn't, what must have happened is that prices, instead of actually initially not reacting a lot, they must be coming down, and output is sort of higher to get this to be ham-shaped. I'll explain the intuition after okay. And then there is another region which we want to discredit, in which it starts to oscillate. Okay? We want to discredit because in this other region, not only it oscillates, the amplitude gets higher and higher, and not only that, but at some critical points, it has no solution, and it goes through poles. So this is a part of the state space that we think that these solutions should not be looked at. Okay? The system is sort of not well. It's like when you have like a quadratic equation and you have like an imaginary root in something and you say, no, I don't like it. It's sort of that type of argument. I could talk more about it, but let me just say that I want to discredit it. This is the region that is on the right-hand side. And again, it not always have a solution. It will go through poles, meaning that it will be very large, and then you change, then there will be no solution. You go and it start from minus infinity. These things are not to be taken, according to us, seriously. Okay, we want to concentrate on the left-hand side. So let me explain the intuition. I think intuition is kind of simple. Let me explain the intuition of the result that may be more surprising, how it could be even ham-shaped. It's actually pretty simple once you think it through it. Why strategic complementarity increase? I think we all understand this. So increases because there is a shock. Some firms are not changing prices because they didn't have the chance. So then you are basically want to be with them. So when you change your price, you change it less. But if this theta is the strength of strategic complementarity is large enough, you not only want to go in the same direction. Remember the case in where everybody's on the right, you want to go to the right? Everybody's on the right. I really want to overmatch them if I have a lot of strategic complementarity. So firms have not adjusted their price enough and not only want to be on the same direction with them, I kind of want to be more than doing that. So they haven't really adjusted price from steady state. I want to lower mine. Okay? And that's why you're going to get a ham shape. And on this region, this is sort of well behaved. So we think that these are solutions that should be looked at. Okay? All right. So and in fact, we have this is a very simple model. You could get a sort of full characterization. So now let me talk about the state-dependent case. So the state-dependent case, it's a case in which you minimize the same object. You take as given this path of x, but now you choose not only the adjustments that you will make, but you choose when to make these adjustments. So now you notice that in the list of objects that you're choosing, there is these taus. So now you choose the stopping times. This is the difference with this case, right? Where the list of objects is only the jumps that you're making. Also here, in this Calvo version, there's no cost. Here, you get to choose when to make adjustment. You choose these times, but if the times do not happen to coincide with the time in which you get the free adjustment opportunity, the tau bars, then you pay a cost, which is the Xi. So for instance, you could choose just to adjust when you have the Calvo opportunity. Or you could choose to adjust there and some other times. Is that okay? So that's the idea. And if the cost is very large, then you will choose only to do it in the Calvo times. If the cost is very small, then you will do it in some way following whatever is the optimal policy. Now let me explain what the optimal policy is. Again, given a path of X. The optimal policy is that you're going to have 3 thresholds. So in Calvo, there was an X star, which was the optimal return point, where to position yourself, right, relative to where you expect the rest of the people to do. Here, there will be something like that, this X star. But there will also be a lower and upper threshold, X lower bar, X upper bar, which if your X is moving randomly, if it hits a lower bar, you want to go to the middle, to the optimal return. If it hits the upper bar, you want to go to the optimal. Is that okay? So if you are outside the interior of the range of inaction, you want to, it's a classical SS, okay? A two-sided SS with an optimal return point, but the bands are changing through time. Why are they changing through time? Because the X is changing through time, the capital X. Okay, so here's like a graphical depiction of it. So they have these 2 bands, then there's the optimal return in the middle, and then this is it's meant to be like a realization of a Brownian. When it hits, you see a time close to 0.1, it hits the lower barrier, then it's corrected and it's sent to the middle, it keeps going. Every time that it hits a barrier, it comes. I mean, this is just a graphical representation of a sample path for given barriers. And these choices, I mean, the choice of the stopping times is equivalent to choose these barriers. And in this problem, the optimal is to have these barriers. Okay. Now let's think about where the capital X comes from. The capital X comes from the aggregation of the decision of every single agent. Here we are trading off the beautifully simple equation that Guillermo described by this one. I think it's beautiful, but perhaps not simple, which detracts from the beauty. But anyway, so there's a cross-sectional distribution M that now we keep to track for every X. This distribution M depends on the thresholds because its support depends on the threshold, and then X star is the return point. So you need to keep track of this entire distribution. The initial distribution, not the initial value of X, the initial entire distribution is given. Okay? And then given a path of M, then you could compute its average by taking this integral at every moment of time. So now you could think about in the equilibrium to have at least the distribution, the lower bound, upper bound, optimal return point, and the average. And what has to happen is that given the path, so that's a condition 1, then the decisions are optimal, meaning that you get your SS bands that are time varying. And given a path of SS bands, then you get the distribution and you compute the average. And these 2 guys have to be the same. In fact, I use the same letter in the beginning of 1 and at the end of 2. That's just a fixed point. The same way that we did in the other model, but here is a slightly more complex object. So I hope that this is okay. How am I doing with time? Okay, not great. So I'm going to consider an MIT shock. I'm going to start at steady state, and I'm going to perturb the steady state a little bit by increasing the stock of money once and for all. That will mean that on impact, wages will go up in this very simple model, and because of that, the whole distribution will shift to the left. The paper goes through the analysis of this. You need to solve all these PDEs. They are related to each other, and you get to a fixed point. That's not to be in the presentation. But the objects that have excess before, they're not going to become, I'm just going to differentiate it with respect to the size of the shock. So I'm differentiating the entire system. The system is a system of equations. They have a continuum index, but you think about like when you differentiate a system of equations, differentiate a system of PDEs. Same principle. So X now will become whatever was at a steady state plus delta times its derivative, which is Z. So X's become Z's. That's my notation. Okay. And now here's the solution. Look at Z star. Z star is how much, it's the cousin of X. Instead of being X, is when there's a small shock, if you take as given the entire path of the X's, which now are called Z's because the deviation from the steady state, is really a forward-looking equation, very much like the one in the Calvo model. The H is not as simple as E of something, but when you end up solving, you do a lot of calculations, you end up solving this, it's an object that cannot discount. Because if you look at the formula for H, which is very nice in the morning, it's sort of look at the formula for H, it's some sort of discount. It has the option value, it has the sigma, it has a bunch of other stuff, but it's basically the same idea, forward-looking object. There is also a similar one for the lower and the upper barrier. The lower and upper barrier, they move in parallel. That's a result. It's not surprising, because the width of the inaction depends on uncertainty, and the shock is deterministic. And that's the formula there. Also, theta, it's only outside, just like it was in the case of Calvo pricing. Theta was outside, and then there was, the integral of the x's. Here is some sort of integral of the z's, so it's kind of very similar. There's some calculations I had to do to get to this, but I'm just skipping them. Then there was aggregation. So in Guillermo, there was this very beautiful sort of ODE that I turned into an integral equation. Here's the same integral equation. This has three parts. The first part is what would have happened if you keep the barriers fixed. And I give you like the formula, at least in the case of Golosov and Lucas. Is this object that is in the bottom pi is not inflation here. It's this 3-point-something number. Okay? Then, but Z0 is what would have happened if you didn't change x's. Okay? Then it has two more terms, and they're backward-looking. Same way that it was backward-looking in Calvo. Again, some operators. And they're backward-looking functions of whatever is the optimal decision. This part is aggregation, the same way that the equation that we looked at Guillermo was aggregation. This aggregation will have some sigmas, it has some other terms, but it's sort of conceptually kind of similar. This doesn't involve theta. Theta only was, like in the other case. So now we put it together. Same way that we put together the two. We substitute, there are three of them, but at the end you put it together, and then you get another integral equation as before. Think of z as a large vector, and k as a matrix, and theta, this number that appears there, just telling you how to. And k has an expression that I always like to say. I find it beautiful, but it's like your kids. You always find it beautiful. Maybe beauty is on the eye of the beholder. All right. So this is, again, if this will be a vector, as opposed to a continuous function, then this is what I put here in bold. This is sort of like a linear system. It's a linear system where k very well behaved. It has all sorts of whatever nice property that you want, it has. Some sort of symmetry, some sort of positive definiteness, some sort of compactness, whatever it turned out to be that it has nice properties, okay? All right, so then you could do something like this, inverted. And when you do the inversion, you could do it by like a Leontief matrix. And what is nice is this k doesn't depend on theta. It has everything but theta. So you could do the comparative static right there. Y0 is what would have happened in a model without a strategic complementarity. So right there you see, if you have a strategic complementarity, you're boosting. And this thing that you're doing powers and powers is this thought experiment that, okay, there's one more run of thoughts. I do this when the rest do that, one more run of thoughts. I do this when the rest have done this twice, so on and so forth. I think that's a mathematical interpretation of this. And you could see as theta is becoming, k is negative, theta is negative, the product is positive. As theta is getting larger, the effects are magnifying whatever happened without a strategic complementarity. So this is stated here. So the fixed point is monotone in theta, higher. Why? Same reasons as before, because the logic is similar as before. It's also true that if you make theta substitutes, the impulse response gets smaller and smaller. If you make it super substitutes, you get to flexible prices. You just go all the way. But there is some critical theta where the solution doesn't exist anymore. Okay, just like in Calvo. But before you get to that, you get hams, just like in Calvo. So let me just show you this in graphs. This is actually the model. This is really Golosov and Lucas. This is the model in which there's no Calvo parameter, and you just hit the barriers. And you looked at them, fix a t, look at the impulse response, you see that they have different values depending on strategic complementarity. So more strategic complementarity, they are higher. Less strategic complementarity, they are lower. Look at the axis. It goes to 1.2. Now I'm going to do the same one from Calvo. The effects are much larger. And there's a sense in which you could show that the effects are 6 times larger. There's a sense, no, you could show that they're 6 times larger. The number 6, no other parameters, like some universal constant. Okay, so you see it's kind of the same behavior, and then there is all the cases in between. Okay? All right, so to summarize this in a simpler way, let me do the following. Let me do the integral, because I want to take the entire impulse response and summarize it in a number. I'm just going to integrate it up to cap t. Then I'm going to compare to what would have been if there's no strategic complementarity. That's this ratio. So I want to see what is the kick of a strategic complementarity relative to the model with a, sorry, Guillermo, but we used to call it with a relative amount of Calvo-ness. So we make it now into like, what is it, an adverb? Yeah, so now it's become also an adverb, which I think is good, you know, sort of like so the relative amount of Calvo-ness will change the C0, but it will also change the CR at theta. So I'm kind of dividing it by whatever the relative amount of Calvo-ness is, and then I plot in this the integral with respect to theta. It goes through 0 by construction, and when you see that as you get more strategic complementarity, this is a particular example, then you have higher. Eventually, this becomes vertical because the solution doesn't exist anymore. It goes through a pole, and it goes to the forbidden region, to a region that shall not be looked at. Okay? Before it goes to the forbidden region, it has a hump, as in the other cases. You know, if you're going to go to a place in which you're exploding, before exploding, you're going to be moving. That's the idea. And this is the intuition I gave you, hopefully the one I gave you before. If you go to the forbidden region for whatever reason, yeah, a question or 1 minute? I think there is a question. So if you go to the forbidden region, it will look crazy. Look at the axis. It's like 200. It should be, if prices will not change, the effect on output should be 1. And also the solutions here will not show up. I could explain why this happened. I'm just saying, we're announcing, as the authors, nobody may follow us, nobody may even read the paper, but whatever, we're announcing that this is the forbidden region. Okay? One more thing, you could also use some version of the Wall theorem thinking that the shocks are IID. Because if you have the impulse response, you could turn it into the word representation, and now you could think about the variance of output. And the variance of output happens to be increasing in strategic complementarity. And you could do this because it's easier to construct the squares. You know, variances are equal to squares. The squares are particularly nice when you are able to diagonalize matrices. And this is a cousin of the diagonalization of matrices. So let me just finish with this. So in this graph, it's the same graph I showed you before, but there are 2 colors. I was told that these are the colors of Barça, for those that know about soccer. But anyway, so there are 2 colors. One is Golosov and Lucas, and the other one is Calvo. And there's all the other cases in between. And you could see that close to 0, again, what is the experiment? I'm looking at the integral of the impulse response. So it's one number to summarize it. I'm moving theta. And around theta equal to 0, around non-strategic complementarity, these 2 graphs we show, they have the same slope. And in fact, in the whole range, they are very similar. There's no more parameters on the rest. It's just a question that we cannot do pencil and paper, so we need to solve it numerical, but there's really no parameters. So the idea is that without strategic complementarity, Golosov and Lucas gives you like a sixth of the effect of Calvo. With strategic complementarity, both of them gives you more, but in a sort of proportional way. You see, because these 2 graphs being on top of each other, since I'm deflating each of them by whatever will be the effect when there is no strategic complementarity, it really means that these 2 effects are sort of separable, multiplicatively separable. So let me just finish. So we think this, I don't know, new method or whatever, some method to study dynamic equilibrium with a G feedback. We apply to price setting with strategic complementarities. Interestingly, either there's no equilibrium or the equilibrium is unique. It's not that there's multiple equilibrium in this setup. We show this approximate separability between price setting and strategic complementarity, and you could use this for some other, for the alert reader, you could see how you could introduce shocks that are announced at time 0 because they are used the same kind of matrix, the same matrix K. So we basically have a companion paper doing the same with arbitrary, as opposed to exponentially looking, arbitrary survival functions. All right, and that's the end of it.
Okay, thanks a lot for having me. It's an honor to be here at the conference in honor of Guillermo Calvo, and it's also an honor to discuss this paper. So I think this is an excellent paper. It makes, in my opinion, a significant contribution to the monetary economics literature. It is extremely dense, as you can see. I say I've absorbed less than a half, and a half I think is a bit generous of what's going on in this paper, but I feel like I learned a lot. What is the question? Well, it's to, again, think about just the propagation of monetary shocks in a GE model with nominal rigidity. So it's not a new question, but what they bring to this are new tools. And the tools that they develop are based on these mean field games that allows them to get all of these analytical solutions and closed form solutions to things that seem impossible to get solutions for. Okay, so why is this a difficult problem? Why is it generally hard to have analytical solutions to the problem that they're looking at? Well, the difficulty really arises in two things. One is strategic complementarity. So firms need to think about when they make their own pricing decisions, they care about the pricing decisions of other firms. That's typically not the case if you use like a CES demand function. So you need to move away from that. And then the other thing that makes this difficult is the forward-looking nature of price setting. So either you do Calvo or you do some Golesov-Lucas menu cost pricing. In those cases, these firms need to take into account the future path of what they want their prices to be, and for that reason, they need to think about the expected path of aggregates. So then that's why you get this seemingly impossible to solve fixed point problem in which the firm's pricing decisions depend on the expected path of aggregates, but these aggregates depend obviously on the individual decisions of these firms, and then basically they solve this using tools from mean field games. Okay, so what am I going to do in this discussion? I'm going to give a very quick overview of the model, and then I'm going to focus on a new result that's not in the paper, but basically Fernando and I have had some discussions about this, and we thought it would be nice to present here. Okay, so it's a continuous time continuum of firms economy. The firm's flow payoff is very simple. They derive it from first principles, but it's basically like the firm cares about their own markup deviation, which is X, and then the average markup deviation, which is big X, and they have some quadratic loss here. And then this parameter theta is just going to be a reduced form for strategic complementarity or strategic substitutability. And again, that can come from some sort of like demand function like Kimball demand where you don't have constant elasticities. And then because of this strategic complementarity, as long as theta is not equal to 0, the firm cares about this future path of xt, big XT, when they're making their own decisions. Okay, so what I'm going to do is I'm going to just take out the Calvo-ness of the model and just focus on the menu cost version. So think Golesov-Lucas, and think of firms that have to pay some fixed cost of adjustment psi when they adjust their price. And so they write down this problem as an optimal stopping problem, but basically you get the optimal rule for the firm in terms of 3 numbers. Actually, these are 3 paths, but basically X lower bar, X upper bar, and X star. And X lower bar and X upper bar are basically going to be this inaction region. Okay, so when X is inside this inaction region, the firm isn't doing anything. They're just letting their XT move around with some, and that's going to be a Brownian motion with variance sigma. Now, when they hit the barrier, then they go to this, they pay the reset adjustment, and they immediately jump to this reset markup, X star. Okay, so the firm solves optimally for these objects, and then from these, you will get obviously a density of firms where inside this inaction region, firms are moving around according to this Brownian motion, but when they hit these barriers, they jump to a reset price, or reset markup, and as you can see, obviously this density is going to have 0 density at the barriers. Okay? Yeah, Oh, and then the main thing that makes this difficult is basically these functions are moving through time. So these are functions of t, and basically the firm needs to be solving for these because they care about what's happening to big xt in the future. Okay, so then they describe the equilibrium as a bunch of equations. I'm not going to go through all of these equations, but an equilibrium in this mean field game is going to be this fixed point, and it's going to consist of a value function u, a density m, and then these functions I talked about before for the optimal decision rule of the firm, as well as the aggregate markup or the average markup. So the x is just going to be that's going to be the cross-sectional average markup. M is a density. X star is going to solve maximize the value function at any point in time. And then there's going to be a Hamilton-Jacobi-Bellman equation for the value function u that's going to describe this u. And then in particular, the strategic payoff, complementarities are coming through these flow payoffs. Remember that. Then there's going to be a Kolmogorov-Forward equation, which basically describes the evolution of m, because again, these firms are moving around inside the inaction region, and then when they hit the bound, they go to this reset price. So they're basically jumping in at the reset price. And then finally, a bunch of boundary conditions. I don't need to talk about these so much, but they're pretty they're reasonable. They make a lot of sense. In particular, like the value at each barrier has to be equal to each other, as well as the value of going to the reset price or reset markup plus paying the adjustment cost. And then the boundaries of these barriers are going to be, the density is going to be equal to 0. Okay. So what they do in this paper is they're able to take these mean field game type of tools and analyze the equilibrium, solve in closed form for a bunch of things. It's kind of amazing what they do. What I'm going to talk about now is a new result. So here's the question. Suppose you solve for the equilibrium and you're in steady state, and now consider a small positive permanent MIT shock to monetary policy. So basically, the firms all on average want to have, say, a higher price. So now what happens to the number of price changes? So by number, I think of like the fraction of firms changing their price per unit time immediately following this shock. So here's some answers. It could go up, obviously on impact. It could go down on impact. And remember, we're in this menu cost model, so everything's endogenous. Like the barriers are endogenous, the firm's choices of when they reset is endogenous. It can remain constant, or it could depend. It could depend on the strategic complementarity. Does anyone want to take a guess? Okay, so it's not obvious. Okay, I would say it's not obvious. I would have guessed maybe it goes up on impact in response to a positive shock. So the answer is it remains constant, okay? And it not only remains constant on impact, according to Fernando, it remains constant on the entire path to the new steady state. So it looks, at the end of the day, like a Calvo model. So this, going back to the conference in honor of Calvo, basically in this menu cost model, you hit it with an unanticipated small monetary shock. If you look at the number of firms changing prices, it's exactly constant as in Calvo models. And in Calvo models, it's obviously by assumption, but here it happens endogenously. So then Fernando tried to explain to me where this result comes from, because, I mean, this is, at least to me, is very surprising. So, okay, so first what you need to think about is how many prices change at any point in time. So forget for a second about the question I asked you. First, let's try to understand how many prices are changing at any point of time. So remember, the firms are changing prices when they hit these barriers, but remember that at the barriers, the density is equal to 0, right? So, you can't just look at the barriers. So what you need to know, and it's pretty intuitive, you need to know the mass of firms that are near the barriers, okay? So obviously you need to know how many firms could potentially touch the barrier. And then you could have, say a huge mass of firms near the barriers, but you don't know how fast they're moving. If they're just sitting there, it's fine. But if they're moving fast, then they're going to hit the barriers more quickly. Okay, so how can we think about this? So it just, for someone like me, it's easier to discretize everything. So let's just think about discrete time. So think of the change in t. Time will just move by delta t, and let's say x follows a random walk. So xt plus delta t is just going to go. It's going to go up with some probability, with probability 1/2 to xt plus delta x, or down with with probability 1/2 by delta x. Okay, and this delta x is just basically approximating this Brownian motion. We're going to keep the same variance sigma. Okay, so to go back to the mass the density I showed you before, you could just draw these kind of like in discrete blocks, and basically in every, these will be of size delta x, and at each point you're going to have some mass there, and with some half probability these firms move left, and with some half probability these firms move to the right. Okay. All right. So now let me zoom in on here, which are going to be the prices. These are going to be the firms that might touch this barrier, hence have a price increase, right? Because they're going to go to the reset price. So if I zoom in on that, let's just look at this mass here. So just go one step away from the barrier to x lower bar delta x. And then basically the idea is, okay, so you have this mass here. Half of them are going to go to the left, hit the barrier, and then move back to the reset price. So now we can calculate pretty easily this number of price increases by unit time, okay? And that's going to be half. Half of those firms are moving. Delta x over delta t is kind of like the speed at which they're moving, the increment per unit time, and then the mass of firms there. Okay, but how do we know what the mass of firms are? Well, you can just then basically do a first order approximation around here. You take, the first order approximation is just going to be this level times the derivative here times this delta x, okay? And so if you do that, what you get is that the mass of firms in that small increment right by the barrier is going to look like this. But remember that this object here is equal to 0, so then you're just left with this mx, just this derivative of the density close to the barrier, or at the barrier. Okay, and then basically what you then get is that the number of price increases is going to satisfy this. It's going to be 1/2 sigma squared times this derivative of the density. Okay, and then by a similar argument, okay, you can do it on the other side. You can do it basically, how many price decreases are there, and it's just going to be this symmetric thing. Sigma squared times mx, this is going to be negative because the density is going down on the other side. Okay, so now let's think about a monetary shock. So the steady state is this is going to be the steady state number of price changes. Those are both the increases and the decreases. And this is the kind of difficult part. So now we're going to consider a small unanticipated permanent monetary shock of size delta. It's going to shift this distribution, right, by delta, because all these firms kind of want to have a delta higher price. Okay, so one thing that is obvious once you say it, but basically wouldn't have been obvious ex ante, is that the width of the inaction region doesn't change. Because basically the width of the inaction region just depends on the amount of uncertainty there is, basically the Brownian motion, but you're not changing that because this is just a once and for all shock. So basically the width of the region doesn't change. And then what they do is they differentiate this density with respect to delta. And then this is kind of the difficult part of the proof that takes time to wrap your head around, and I don't fully get it yet. But basically, what you now do is, so you call this n you differentiate this density with respect to delta, and then because it's a small shock, you can basically think about this at delta equal to 0. And then this means the density is equal to this steady state density plus this delta times n. And then if you go back to the equation we had before, you just differentiate that at the barriers with respect to x. And what you can show is basically that this n, or what Fernando could show, is that this n is anti-symmetric, which means on either side, they're just equal to the negative of each other. And then that implies that n itself is symmetric, which means that if you look at this derivative we had before, that's the steady state number of price changes. And this is now how the density changes with respect to this delta. Those two things cancel out. And basically, it just means that you get back to the number of price changes being the same as what we had before. Okay, so that's kind of the heuristic proof. And this tells us that basically, the implication here is that the number of price changes does not respond to a monetary shock in a model that did not assume Calvo. Okay, this is a model that's completely endogenous in terms of when firms change their prices. And that just means that there are more price increases, but there are less price decreases, and then they exactly cancel out each other so that you basically get the same prediction as in the Calvo model. And the implication of this is that if you go to the data, if you want to distinguish Calvo from, say, a state-dependent menu cost model, you can't just look at the frequency of price changes in response to these small shocks. Basically, you would have to either look, because they are going to have the same prediction, you'd have to look at large shocks or the size of price changes. And this is something we wouldn't necessarily know without this type of framework that Fernando and his co-authors have built. Okay, so just to conclude, this is an exciting, significant contribution to the monetary literature, develops new methods for solving these models with strategic complementarities, and I would definitely say that graduate students interested in this literature should start learning these new tools.
Thank you very much, Jennifer. We have very little time, but if anybody has a pressing question, I'll take it. Yes.
Jim Bullard, St. Louis Fed. So I love this paper, and I thought it was great. So I have a new title for you. State-dependent pricing is actually Calvo pricing after all. And I think that's an exciting result. But I would extend that title a little bit. State-dependent pricing is actually Calvo pricing after all in normal times. And I would like to hear how you would interpret the pandemic inflation that we have, which would be a classic example of a big shock where Calvo pricing seemed to break down, and should we try to infer from Calvo pricing type models in that situation? And I think the answer is probably no. So is that the correct takeaway for a policymaker from this?
So first, I just want to thank Jen for like an amazing and overly positive discussion. Also, I just want to say that when I told Jen that I was working with Takis, she told me that she knew Takis, so I was sort of happy because she was a classmate of Takis' daughter. Anyway. All right, so so we wrote a paper called Are Time-Dependent and State-Dependent Models Differently? And they differ by a magnitude of 6. So they don't differ because of the frequency of price changes, but their selection between the price changes makes that the speed, even if the frequency of price changes is the same, the speed to where you go after a shock is much lower in Calvo, and it means that the area under the impulse response is 6 times bigger. So there is a difference, but it's not to be looked at here. And that's, I think, is what I said about this small set of models that we looked at. But the other thing is that we looked at, now we have looked with Andy before, with Andy Neumeyer, at large cost shocks in Argentina, which is a fantastic source of monetary experiments. We have looked at now the UK, the microdata from the UK. We have looked at the microdata from the US. And we could also go back and look at Gagnon data from Mexico. We could look at the Emis and John data from the US before. And what you see is that when there are large shocks, there are changes in the frequency. So I think that this is sort of saying, I think for like small shocks, this is a lot of work just to get the selection right. But for large shocks, I think that we see the evidence because all things that we did and Jen explained was for very small shocks. For large shocks, you have higher pass-through because you do have a change in the frequency. So, which I think is what you were saying, no? But I just wanted to.
Yeah, just to follow up, so the Fed talks to a lot of people on the ground about their pricing, and it's totally obvious that when the big inflation came, they started saying, hey, we're going to review our pricing decisions every month because we don't know what the heck is going on, and there are all these supply constraints, all kinds of things going on. So it sounded very, very state dependent, but that is not consistent with the main theorem here, I guess. Because, no, you're just looking for a small shock, for a small one-time shock.
The theorem is for a derivative around zero.
Okay.
Small shock, a large shock. Oh, sorry. The theorem is for a derivative with respect to the shock when the shock is equal to zero. When you do, suppose that the width of the barriers is 10%, just to make it simpler. Suppose you have a shock of 20%. Just to make it simpler, then every single firm will change prices. But if you have a small shock, all these effects, they cancel each other. So it's, anyway. So we actually looked at the shocks for Argentina. Well, I guess the density of RGs in this room is alarmingly high, but a lot of us, we know about the changes. Well, anyway, there's a lot of stuff going on in Argentina, let me just say.
Thank you very much, everybody, for a great session. So we're moving now next to the next session. Let's give them a round of applause.